Using our same example VAV air handling unit with this discharge configuration, the housed airfoil fan requires 11.8 brake horsepower compared to 14 for the belt drive plenum fan and 12.8 for the direct drive plenum fan. While the housed fan requires less power, the plenum fans will typically have significantly lower discharge sound levels. The reduced sound levels occur partly because air velocity dissipates more quickly as the air pressurizes the plenum surrounding the fan, and because the plenum provides an opportunity for some of the sound to be absorbed before air discharges from the unit. The direct drive plenum fan reduces sound levels even further because it does not have the belt-related drive losses and associated noise, and because there are no obstruction in the inlet and the motor is mounted behind the fan wheel, it does not restrict airflow leaving the fan. Of course, this chart compares discharge sound. On the inlet side, plenum fans will usually have higher sound levels than housed fans. So depending on the fan's location within the air handling system, either discharge or inlet sound may be more important. So the best fan choice depends on the application.
So, if the air handling unit has a draw-through fan that discharges directly into a sufficiently long, straight section of duct that's about the same size as the fan outlet, a housed airfoil fan will typically require less power than a plenum fan, but a plenum fan will likely have lower discharge sound levels. Let's look at another example. A discharge plenum is often added downstream of a housed fan to reduce discharge sound levels or to provide more flexibility, like multiple duct connections or to allow for an abrupt change in direction. But as I mentioned, a housed fan is at its best when discharging into a straight section of duct. When a housed fan discharges into a plenum, the energy losses result in increased fan power.
In our example, adding the discharge plenum to the housed fan increases its brake horsepower from 11.8 to 13.2 since it no longer discharges into a straight duct. This is still lower than the belt drive plenum fan, but now the input power for the housed airfoil fan is higher than the direct drive plenum fan. But adding the discharge plenum does allow the housed airfoil fan to achieve similar discharge sound levels that are fairly close to the plenum fans. In this example, the direct drive plenum fan is still the quietest, especially in these low frequency octave bands that are difficult to attenuate.
So, when a discharge plenum is added to a draw-through housed fan, it results in more fan power being consumed, typically to the point where a direct drive plenum fan has about the same power consumption as the housed airfoil fan. And discharge sound levels are similar, if not better, with the plenum fan. But the air handling unit with the plenum fan will likely be shorter. In this example, adding the discharge plenum to the housed fan increased the overall length of the air handling unit by more than 3 feet. When multiple supply duct connections are desired, a housed fan requires a discharge plenum to allow for the multiple connections. With a plenum fan, multiple duct connections can be made to the fan section itself, eliminating the need for a discharge plenum and resulting in a shorter unit. Due to installation restrictions, it's often unlikely that a housed fan can be installed in the ideal configuration as shown in example 1. This makes the use of discharge plenums and multiple supply duct connections fairly common. Let's look at one more example. In some applications, final filters are included as the last section in the air handling unit.
When a housed fan is used, a diffuser section must be added downstream to provide even airflow through these final filters. This is not a requirement for the plenum fan since it pressurizes the surrounding plenum and provides even airflow through the filters with minimal downstream distance. In this configuration, the input power for the housed fan increases due to the pressure drop of the diffuser and the fact that the housed fan is no longer discharging directly into a straight section of the duct. For our example, the direct drive plenum fan requires the least amount of power, 14.1 horsepower compared to 15 for the housed airfoil fan.
Let's summarize this discussion of housed versus plenum fans. When discharging into a single, sufficiently long, straight section of duct that is about the same size as the fan outlet, a housed fan will likely require less power than a plenum fan, but a plenum fan will likely have lower discharge sound levels. If a discharge plenum is added downstream of a housed fan to reduce sound levels or to allow for discharge flexibility, a direct drive plenum fan will likely require less power than a housed airfoil fan, with similar or superior discharge sound levels. Additionally, the plenum fan will likely result in a shorter air handling unit. When downstream sections are present, such as a discharge plenum, final filter, gas heater, or even a blow-through cooling coil, a direct drive plenum fan will likely require less power than either a housed or belt-driven plenum fan. Before we leave the discussion of plenum fans, let's discuss the use of direct drive rather than belt drive plenum fans, which have been allowed for some changes to traditional paradigms when selecting the fan. Historically, the diameter and width of the fan wheel would often be predetermined by the fan manufacturer of the air handling unit. The variable open to change was the rotational speed of the fan shaft, or RPM, which was adjusted using belts and sheaths. Today, direct drive plenum fans are available in various wheel diameters and wheel widths. Even though there are no belts and sheaths to adjust speed, the fan can be operated at various speeds by a VFD. In a sense, the VFD on a direct drive plenum fan replaces the drive kit that would be used for a belt-driven fan. Most people think of a VFD as being used to reduce the speed of the fan, from the motor synchronous speed to some minimum turn-down limit of the VFD. However, the VFD can also be used to operate the motor above synchronous speed. This provides the opportunity to use one of two selection approaches. The first, which we'll refer to as synchronous speed selections, operates the motor at its synchronous speed, typically 1800 or 1200 RPM. The diameter or width of the fan wheel is then changed to achieve the desired performance. Flexible speed selection is a relatively new concept in the industry. With this approach, the width of the fan wheel is held constant, and the diameter or speed of the fan is then changed to achieve the desired performance. As an example, the VFDs and motors that Trane uses for direct drive plenum fans and air handling units can operate up to at least 90 Hertz, which equates to about 2700 RPM for a nominal 1800 RPM motor. Flexible speed selections typically allow for a more efficient and quieter fan choice. Let's look at an example.
Using the same example VAV air handling unit, here are two selections for a 30-inch diameter direct drive plenum fan. The first row shows a synchronous speed selection, and the second row shows a flexible speed selection. For the first selection, the motor's nominal speed is 1800 RPM. To deliver the desired airflow and static pressure, the width of the fan wheel is trimmed down to 57% of nominal width for this particular wheel diameter. And the motor operates at its synchronous speed of 1780 RPM. For the flexible speed selection, however, the fan wheel is kept at its nominal width. To deliver the same desired performance, the fan wheel need only rotate at 1320 RPM. Here we can use a 1200 RPM motor and operate it above synchronous speed by running the VFD at about 66 Hertz rather than at the nominal 60 Hertz. The resulting input power drops from 15.4 horsepower for the synchronous speed selection to only 12.8 for the flexible speed selection. And because the fan operates at a reduced speed with a wider wheel, the flexible speed selection will typically result in lower discharge sound levels.